All right, today we're going to continue talking about probability, but in this lecture we're going to restrict our attention to just uniform sample spaces. Okay? Uniform sample spaces. So you know what a sample space is, right? It's all the possible outcomes. It's a set of all possible outcomes. And a uniform sample space is a sample space in which each outcome is equally likely. So, for example, in our coin toss, right, our sample space consisted of heads or tails. Those were all the possible outcomes. And so that would be a uniform sample space because it's just as likely to get heads as it is tails. Okay? So when we have a uniform sample space, the nice thing about that is that we can use our counting techniques that we learned in Chapter 6 in order to determine probability. What we need to know, the probability of an event, then, is just the number of elements in that event over the total number of elements in the sample space. All right, so let's go ahead and look at example 1. I think it'll make more sense once you see it in action. So in example 1, we've got an unbiased coin, and we're going to toss it 6 times. And we want to know what the probability is of that coin landing so that we get exactly 3 heads. Okay, that's the first question anyway. We want to get heads exactly 3 times. All right, so now that could happen any number of ways, right? We could get heads, 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 tails, tails, tails. But before we get even started with that, we first of all need to know how many elements are in our sample space. How many possible outcomes are there, right? We need this n of s, right? And the number of elements in the sample space. So just think about how many ways that the coin can land. We're just going to use the multiplication principle. We've got 2 possible outcomes for the first time we toss the coin, and 2 outcomes for the second time, 2 outcomes for the third, and the fourth, and the fifth, and the sixth, right? And so we just get basically 2 to the 6th power, which is equal to 24. 24? What? Wait, hang on a minute. 64. Right, you kind of just have to count up. 2, 4, 8, 16, 32, 64. Okay, so 2 to the 6th power. So now we have the total number of outcomes, for a sequence of tosses. Okay, the sequence is important because we're going to assume that the order matters, because that allows us to have a uniform sample space. Okay, so what we want to know is how many of those outcomes have exactly 3 heads. All right, so we're going to define an event E. We're going to say, let's let E be the event that includes, well, it's going to include H, 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 T, 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 right? Our desired outcome, or our desired event is exactly 3 heads. But there's a whole bunch of different ways we could write that, right? That's one way, H, 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 T, 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 right? We could get heads on the first 2 tosses, and then the tails, and then another heads, and a couple more tails, or any number of ways, right? That could just go on and on. But we don't really care about what the event, we don't have to list it all out in roster notation, but we want to know how many elements are in that event, okay? So we've done this problem before. If you remember, we can think of it like a letter arrangement. Right? We've got 3 heads and 3 tails, and we just want to know how many different ways we can arrange those letters, right? So the number of elements in the event that we're interested in is going to be 6 factorial, because there's 6 letters, and we're going to divide by 3 factorial times 3 factorial, okay? Because there are 3 H's and 3 T's. All right, so we can multiply all that out. 6 times 5 times 4, times 4. 4 times 3 times 2 times 1 over 3 times 2 times 1 times 3 times 2 times 1. Okay? And let's get some cancellations. We can cancel 3 times 2 times 1 with the 6, so we end up with 20 ways. All right? And then when we want to calculate the probability, we're just going to take that, the probability of the event is going to be the 20 ways to get 3 heads over 64 total ways that we could, that the coin could, 64 different sequences of heads and tails that are possible. Okay, so if we reduce that, we get 5/16, or we can just put it in our calculator and get a decimal. So 0.3125. All right. So we could also write that as 31.25%. But you know that probability ranges between 0 and 1. So 31% probability or 0.31 probability is a fairly low chance, right? So one other thing I want you to notice here is that this 6 factorial over 3 factorial times 3 factorial is actually 6 choose 3. It is a combination 6 choose 3. So you could think about it in terms of you've got 6 different letters that you've got to arrange, or you've got to fill with H's or T's, and you want to choose 3 of them to be H's, and then the rest are just automatically going to be T's. Okay, and it doesn't matter what order I choose those slots, those spaces to fill. You know, if I choose this one and then this one and then this one to fill with H's, it would be the same as if I had chosen this one and then this one and then this one. Okay, so it's interesting that it turns out to be the same thing. This is just a combination of 6 choose 3. Okay, just want to point that out. That in this particular case, because we only have 2 options, H and T, that the permutation with repeated elements that we're using, the letter arrangement problem, turns out to be exactly the same as a combination. All right, so we've calculated the probability of getting exactly 3 heads. All right, so part B asks kind of a variation of that problem. All right, what's the probability that we get at most 3 heads? All right, now we have to break this one down. So we have to think about what does that mean, at most 3 heads, right? At most 3 heads would be no more than 3. So 0 heads, right? That would be no more than 3, right? Definitely less than 3. 1 head, right? 1 head would be definitely less than 3. 2 heads, or 3 heads. Okay. So what we need to do, we've got all these different cases. We could get exactly 0 heads. We could get exactly 1 head. We could get exactly 2 heads or exactly 3 heads. And the nice thing about that is that when I break it down in that way, all of those different events are disjoint, right? We can't have exactly 1 head and exactly 2 heads the same time, right? So that allows us to add the number of elements in those different events. If I break them down this way, where we've got exactly 0, exactly 1, exactly 2, and exactly 3 heads. Okay. So what do we need to do to find that? Well, because I just said we can think of this as a combination problem. We've got 6 slots to fill, right? And we're going to choose 0 of them to be heads, right? We can think of it like that. And 6 choose 0 is equal to 1. And that would just be the event where you have all tails. Okay. If we want the number of ways that we can get exactly 1 head, we can think of it as 6 choose 1. Okay. So if you think about that, you would have, your events would look like I have 1 head and all the rest are tails, right? So just think about where you could put the head. You could put the head in the 1st position or the 2nd or the 3rd or the 4th or the 5th or the 6th position. So essentially you're going to get the 6. You don't really have to calculate it out. I mean, you could, because it's just going to be 6 over 1, but there's 6 different ways to get 1 head. Okay. 6 choose 2, right, would be the number of ways that you could get 2 heads, right? We're just going to choose 2 of our slots to fill, And we're going to put heads in those slots, and we're going to fill the rest with tails. Right? So 6 choose 2 is, what is that? So it's 6 times 5 over 2 times 1. So that gives me 15. If I want exactly 3 heads, we basically already calculated that, right? Exactly 3 heads is 6 choose 3, and we calculated that already to be 20. Okay. So now we have all of the ways to get 0 heads, 1 head, 2 heads, or 3 heads, right? Those would all qualify as at most 3, right? And they're all disjoint sets, right? So there aren't any overlapping, we can't get any of these events at the same time. And so all we really need to do is add. So what do we get? We get 1 and 6 is 7, so that's 22. So it looks like I get 42 ways. And that's our number of elements in the event that we're interested in here. If we just make, I'm using E again, but I'm defining it as a new event where we get at most 3 heads. Okay. So now we're going to calculate the probability. So what's the probability of this event? Well, we need the number of elements in the event that we're interested in, which we said was 42. And we're going to divide by the total number of possible outcomes, which is 64. Okay. So I could reduce this to 21 over 32, or I can just calculate it as a decimal. So 0.6563. Okay, so that's my probability. I want to point out too that another good way to get combinations, especially if it's small numbers, is to use Pascal's triangle. Okay, we talked about this in chapter 6. I talked a little bit about Pascal's triangle, and it's really easy to create, right? You're just starting with a row of 1 ones and then 2 ones and then 1, and then you're adding the numbers above to get the number below, right? So that's how I'm getting 1 2 1 and then 1 3 1. 3's come from 1 and 2 and 2 and 1, right? 1 4 6 4 1 1 5 10 10 5 1, and then 1 6 15 20 15 6 1. And this last row that I wrote is 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, and 6 choose 6. Okay, so this basically is all my combinations right here that I'm interested in, that I just calculated. So without a calculator, you can easily get your combinations straight from Pascal's triangle. All right, that was kind of an aside. Let's finish this up here. What's the probability of getting heads on the first and the last toss? Okay. Well, we need to figure out how many ways that can happen, right? Our event is heads on first and last toss. So let's just use the multiplication principle on this. So if we're going to get heads on the first toss, right, that's only one option, right? Heads. On all of the other tosses, or at least the second and the third and the fourth and the fifth tosses, we still have our same 2 options. But then on the last toss, we have to get a heads. So there's only one option, right? So basically we just have 2 to the 4th if we restrict the first and last toss to being a head. So that gives us 16 different ways that could happen, just using the multiplication principle. So the probability of that event happening is 16 out of 64, which is 1/4, which is 0.25, or 25% chance, 1/4 chance. Okay. All right. Well, this is where you might want to stop the video and try this yourself. We did exactly 3 heads up here, right? And so this one's asking, what's the probability of getting exactly 4 heads? So you can pause the video. Otherwise, I'm gonna go ahead and go through it. All right. So we want to know how many ways can this happen? How many ways can we get exactly 4 heads? All right. So think about if you think about it in terms of you get 6 slots to fill, and you're going to fill 4 of them with H's. The rest are just going to be T's. It's going to be essentially 6 choose 4, right? 6 slots. You're going to choose 4 of them, and the order doesn't matter. The order in which you choose the slots doesn't matter. Now, 6 choose 4. If you think about our combinatorial identities that we talked about again in chapter 6, 6 choose 4 is the same as 6 choose 2. But you don't have to remember that. It's easy enough to calculate 6 choose 4. So if I do 6 choose 2, it's just 6 times 5 over 2 times 1, which is 15. Right? And I already calculated 6 choose 2 anyway. Or you could have come up to Pascal's triangle and gotten 6 choose 4 or 6 choose 2 from Pascal's triangle. Right? You just count over, so that's 0, 1, 2, 3, 4. So this is 6 choose 4. Okay. And then once we've got the number of elements in that event, we're just going to take we're going to find the probability of that event by taking the number of elements in the event we're interested in over the total number of events in this sample space. So 15 out of 64. Put that in my calculator and I get 0.2344, or about 23.44%. All right. Well, I will meet you in the next video to do some more practicing.